Hello everyone, welcome to the course Geotechnical Engineering 2. So in this lecture number 3, we will be discussing on the stress system considering the planes not as principal planes. So myself SSS Nitish, Assistant Professor, Department of Civil Engineering, Vigyan Institute of Information Technology, Duvada. Okay. So in this particular lecture or in the previous lecture, we have discussed some of the basic mechanism to shear strength. So here this lecture is a continuation to this part. Okay. So what we will do is, in the previous session we have learnt about a particular homogeneous two-dimensional body having the stresses sigma 3 and sigma 1. Okay. So these two are the principal stresses acting on the principal planes. So we will be learning in detail about these in that particular lecture. So now similarly for this particular case, okay, we have obtained the relationship for the stress, okay, the normal stress on the failure plane AB as well as the shear stress on this particular plane AB. So that using these two we have obtained the failure shear stresses, that is shear stresses and normal stresses. Okay. So in a similar fashion, now we will try to understand the same case, but when these two planes, that is the horizontal and vertical planes, are not the principal planes. Okay. So let us say in this session, so let us consider a two-dimensional body. Unlike the previous case, now we will be considering the stresses as sigma x and sigma y. Okay. Sigma x in the horizontal direction and sigma y in the vertical direction. But these horizontal as well as vertical planes, whatever are there, these are not the principal planes, that you need to keep in mind. Okay. So in a similar way, we will assume a particular plane making an angle theta with the horizontal, and then we will denote them with A, B, C, D. Here you need to remember one thing, apart from these, since these are not principal planes, here additional stresses tau xy will act on the surfaces of these boundaries. Okay, that you need to keep in mind. So that is the major difference between the previous session and today's session. So a detailed diagram in the wedge form for resolving of forces, just like the previous case, we will be considering, and similarly we have to find out this tau as well as sigma for this particular case. Okay. So now coming to today's lecture. So you can see the title here, as it has mentioned, the stress system with vertical and horizontal planes not as principal planes. In the previous session we have discussed that these are the principal planes, but now these are not the principal planes. So as I have stated, as these are not the principal planes, if you see in this particular diagram, if this is a three-dimensional body, the surfaces, the surface 1, the surface 2 as well as the surface 3, okay, these surfaces are not the principal planes unlike the previous case. So similarly we will be considering a two-dimensional system instead of a three-dimensional body, as we neglect the intermediate stresses. So that is why we consider a two-dimensional body just like the previous case with x and y axis as the coordinate axis, and we neglect this z axis. Okay. This is how we use the same method to derive an expression for sigma and tau on the failure plane for this particular case also. Okay. Let us look at this in detail. Now let us consider a two-dimensional homogeneous soil mass having both horizontal as well as vertical stresses as sigma x and sigma y, and then we will be considering, let us say there is a failure plane making an angle theta with the horizontal, and let us denote in the wedge form also. Okay. So apart from these, let us consider additional stresses, shear stresses on these surfaces, that is tau xy acting along this plane. Okay. Now I have represented these in the same way. Let us denote the wedge as A, B, C. Okay. Now considering the equilibrium of forces once again, now we need to evaluate this sigma and tau. So if you consider the equilibrium of forces, and if we consider the resolving of forces along x direction, okay, so let us consider at this particular point, okay, at this particular point we have to consider the resolving of forces. Okay. So if you see along the horizontal direction at this particular point, this sigma can be resolved as two parts. Okay. If this is theta, then this will also be theta, and this particular region between sigma as well as this horizontal line is 90 minus theta, therefore this angle will again be theta. So using this, what will be this particular one now? This will be sigma cos theta, okay, and this will be sigma sin theta. So since we are resolving along the x direction, we only require this. So that is why I have written sigma sin theta, which is acting on the plane AB. So this will be sigma AB sin theta, clear? So in a similar way, apart from sigma, we have sigma x. Sigma x is acting on BC, so it is sigma x into BC, plus if you see the shear stress tau xy is acting in this direction. So again we can represent this as tau xy into AC. Similarly, this will be tau. If you resolve the tau that is acting here, say if you resolve the tau that is acting in this manner, then this will be again along the horizontal direction, it will be tau AB cos theta. So you just try to resolve this on your own. For simplification, I have just given the direct formula here. So if we simplify this, okay, by dividing with respect to AB again, so we can simplify that this is sigma sin theta, which is equals to sigma x sin theta plus tau xy cos theta plus tau AB cos theta. So you have to use this expression when resolving along the x direction. Similarly, if you resolve the forces along y direction also, you can simplify, you can simply get an expression using this wedge, okay. Now you have to simplify this by dividing this with respect to AB once again. So if you divide this, you may obtain at some other expression. Let us say this is equation 1.4 and the previous equation is 1.3. So now using these two equations, we need to obtain a formula for the shear stress as well as the normal stress on the failure plane, okay. We need to find out the shear stress and normal stress on the failure plane using these two expressions, okay. Now, so how do we do it? So by solving these, just for our consideration, I have given the wedge once again. So using the equations 1.3 and 1.4, if you solve those two by squaring and adding, you can simply conclude that after a lot of steps and procedures, you can finally obtain at this location where you get sigma and tau value for this particular failure plane, clear? In that way, we have to evaluate this normal stress and shear stress for the failure plane, clear? Now, one thing you need to remember. So if you look at these two expressions are in the form of, say this is x and this is y, okay. So what happens, these sigma xy or sigma x or sigma y or tau xy and theta, these are the known entities. So since these are known entities, this will be a certain term, okay. So what happens when you do x square plus y square? So that will be a known entity here. Say it is r square, so it is a known entity. That means this equation what you are obtaining by squaring and adding is in the form of a circle, okay. So that is why if you consider for the same case, let us say this is sigma square plus tau square, then this is capital R square, okay. So this equation is in the form of a circle. So if you represent this on a tau and sigma plane, then this will be a circle on that particular plane. So this circle is known as Morse circle. So this we have discussed in our previous session anyway. The only thing that is changing is here the stresses that are acting. In the previous case it is principal stresses, now it is a normal stress, clear? So using these equation, if I draw a circle, then it will have a particular radius here, okay. If you see, the radius will be sigma y minus sigma x by 2 whole square plus tau xy whole square whole power 1 by 2. So this will be the radius of that circle that is obtained. Similarly, the center of this circle will be at a distance of sigma x plus sigma y by 2 comma 0, okay. So in such way we need to evaluate the Morse circle, its center and radius. Finally, so if you have to locate any particular point, on that circle, say I am marking a particular point on that circle, let me represent it here for your clear understanding. So if I have to draw a circle and I represent any particular point let this is tau and this is sigma. If I have to represent any particular point on the circle, then that point represents the stress on a particular plane having theta and sigma and tau as the coordinates. Okay, that you need to understand. Now, so finally, whatever we have obtained is nothing but my Morse circle. Now, so coming to the construction of a Morse circle, how do we construct this Morse circle? Apart from this analytical thing, whatever we have done till now, so let us try to understand how do we draw a Morse circle, or how do we understand the graphical representation of a Morse circle. So initially, so let me consider the sigma and tau axis. Okay, so here you need to remember that the only thing I know is sigma x, sigma y, theta and tau xy. That is your given data. Okay, so using these stresses, external stresses, sigma x, sigma y or tau xy that are acting, we need to determine the Morse circle. How do I do that? So first you will be taking the x coordinate as sigma axis, y coordinate as your tau axis. Once you have done this, you have to represent your values of sigma x and sigma y. Take the scale as the same. Okay, let us suppose sigma x is at point Q. Okay, let us say it is at point Q and sigma y is at point R. Okay, so you need to mark this on the sigma axis, and then using the shear stress, that is tau xy, you need to represent them on the graph. That means using the tau xy, draw a horizontal line at this particular point, and at this particular point R you draw a vertical line downwards. Let us say this is Qs and this is Qt. The scale should be same for sigma as well as tau. Okay, imagine this is sigma x is 40 and sigma y is 80, and say your tau xy is some 20 kilonewton per meter square. Okay, so if you mark this, all the units must be in the same scale. So then you will obtain at this particular thing. So what you will do? Then you need to join S and T. Okay, if you join S and T, it will intersect the horizontal axis at a particular point known as C. Okay, so this point C is the center of our Morse circle. Okay, so using this particular point, we have to obtain our Morse circle. So there are two methods how we do it. Let us see. So let me just draw the diagram once again for our understanding. So if you look at this particular diagram, so this is tau xy, this is sigma x, this is sigma y. Okay, so what we need to do now? We need to, using this point C, we need to draw the Morse circle. So this you can either do it by a simple method, you do the analytical approach method, you calculate the radius of the circle using the formula that I have mentioned earlier. You using this radius, what you will do? Using a compass, you try to place it at the center and draw a circle. Okay, then you will get a particular circle. So this is a Morse circle, or else you may simply take SC or CT as the radius and you can simply draw the circle. So these are how we draw the circle. So here one thing you can cross check is that using analytical method, if you can draw a circle with C as the center, then you can clearly observe that the circle will intersect at S and T. Okay, if you using the analytical radius what you have obtained, if you place your compass with C as the center and if you draw the circle, then it will intersect at S and T. So this is your check that you can carry out. Now here another thing, how do I find out my principal stresses in this case? Okay, so if you look at this particular diagram, this circle which is intersecting at this sigma axis at these 2 points. Okay, so the point at which, the major point at which it is intersecting at the sigma axis is denoted by sigma 1. That means that is your major principal stress. Okay, this is where the circle is intersecting your sigma axis. Similarly, it will intersect at some other value which is smaller, so that will be your minor principal stress. So this is how you evaluate your major principal stress and minor principal stress. So there is one more entity. If you see, this is the maximum radius of the circle. So if you see at the vertical line, say this is the maximum value of your shear stress. For any particular stressed body, you can obtain at a maximum shear stress, that is tau max. So that will be equal to your radius of the circle. Okay, So, in such way we need to evaluate our maximum shear stress. So, another thing, so there is a point known as, or a concept known as pole. So, to understand this, I am just taking the same diagram what we have considered, the two dimensional body, along with a failure plane making an angle theta. Okay. So, how do we find out the pole? What is meant by pole? Okay. So, if you look at this particular diagram, pole is a point. Okay. Pole is a point on this particular circle. Okay. So, how do we find out this? If you draw a line either parallel to this, okay, if you draw a line along the failure plane which is parallel to this and intersecting this circle at a particular point, okay, if it is intersect at a particular point, then that point is known as your pole. Okay. So, that point is known as your pole, and it always makes an angle 2 theta. Okay. This always makes an angle 2 theta with your ST. Clear? Now, so that is how we determine our pole. So, let me clearly explain some of the important characteristics of this Morse circle. So, let us proceed to this. So, for our understanding, I am just neglecting all the other parameters and I am simply writing sigma 1 and sigma 3. Okay. And let us say D is a point which is the pole. Okay. So, if you look at, as I have mentioned, this tau max. So, what is the maximum value of the tau max? It is nothing but it is the radius of the circle. So, if you look at this diagram, the radius of this circle will be sigma 1 minus sigma 3 will be the diameter. Okay. Sigma 1 minus sigma 3 will be the diameter, half of it will be the radius. So, sigma 1 minus sigma 3 by 2 will be the maximum shear stress that can occur. Okay. So, in general, if you consider the two dimensional body which is stressed in all the directions along with shear stress, the maximum value, okay, the maximum value of shear stress can be obtained on a plane, okay, on a failure plane which is inclined at an angle of 45 degrees. Okay. Imagine this is a particular plane, okay, and it is completely stressed body due to external loads, along with say shear stress is also applied. Okay. Shear stress is also applied. So, there occurs a particular failure plane which is actually inclined at an angle of 45 degrees. Okay. This angle is 45 degrees. This angle is 45 degrees. So, on this particular plane you can observe the maximum shear stress. So, that is what you need to keep in mind. Coming to the other part. So, as I said, D is a particular point which is representing a particular pole. So, here you need to understand that when a plane is making at an angle of theta, so let me just draw it here. So, imagine this is my particular planes. Okay. So, this is making an angle 2 theta. Okay. So, whenever this particular point is making at an angle of theta, that is known as my major principal plane. Okay. So, this particular point on this graphical representation will be at a particular distance and at an angle of theta with the major principal plane. Okay. This is one of the important characteristics. So, that is how we find out our major principal plane. So, in this particular case, if you look, say this is making an angle theta here, then this particular region will be my major principal plane. So, that is one of the important characteristics. So, how do we find out the minor principal plane? Major principal plane and minor principal plane are always perpendicular. Okay. You can obtain from that particular thing. Apart from that, so if you look at, let us consider there is a small plane. Okay. There is a small plane. If you observe this tangential plane which will intersect at a particular point on the Morse circle, let tau f be the shear stress at that point. Okay. And this plane which is making tangential to this particular Morse circle is known as the plane of obliquity, and this particular plane having shear stress tau f will always be less than tau max. That you can clearly see from our diagram itself, as this will always be less than tau max because it has to pass through the center as well as intersect the circle. Okay. So, that is why tau f is always less than tau max. So, this is one of the important characteristics. Let us try to understand this particular Morse circle which I have considered previously. So, if you see here, another characteristic is that this point SQ and ST. You may be wondering why I have drawn the shear stress upwards and other one downwards. Okay, because for our convenience we need to consider the shear stress at one region as positive and the other region as negative. So that is why here shear stress may be opposite in sign. Okay, when you are drawing a Mohr circle, the shear stress may be opposites in sign, but you need to remember that these are numerically equal. So that is why whether it is positive or negative, that means the positive or negative indicates here the direction of the shear force acting on the plane. Okay, so that is why it may be either positive or negative, okay, in a particular plane itself, but it will be numerically equal. So that you need to keep in mind. Now apart from that, here if you look at this circle is actually symmetrical about this sigma axis. So that is why in general practice what we consider is we may just neglect the bottom half and we may just draw the upper half of our Mohr circle. Okay, this is one of the important characteristic again. And then regarding the sign convention, what I have mentioned, we do not need to be rigid because anyway these are numerically equal. To find out the resultant, what we will do, we will be finding out anyway or sigma square plus tau square. So that is why we do not need to be rigid about these particular sign conventions. Okay. Now, so here I have mentioned some of the assignment questions just for your practical understanding. Just make sure to just derive this particular equation whatever I have mentioned now for your more detailed understanding. If you have any clear queries or anything, you can just go through your reference books and textbooks. Anyway, we will be providing you with the material and we can help you out through clarifications. And then furthermore, I have mentioned one particular problem here. Just let us look at this particular problem. If you look at the normal and shear stresses, I have given the normal and shear stresses acting on a particular plane are so and so. Let us say this is 80, let this be sigma y, okay. Let this be 60 be sigma x and this 40 be tau xy, because it is respectively given as normal stresses and shear stresses. Now we need to determine on a particular plane which is at an angle of 30 degrees, that means theta is given 30 degrees, we need to find out the normal, shear and resultant. That means we need to find out sigma, we need to find out tau and we need to find out the r. These are the resultant stress. So now apart from this, it is further asked that also determine the center of the Mohr circle. Okay, we know what is the center of Mohr circle and what is its coordinates. Okay, previously we have discussed. And similarly the radius of the Mohr circle also, that also we have the expression what we have derived now. And then finally the maximum shear stress analytically. So what is the maximum shear stress? It is nothing but my radius of the circle, simple logic. Okay, so this is how we just obtain a Mohr circle. And then furthermore I have mentioned here, just use the same question number 1 and you try to draw the Mohr circle using graphical representation. Okay. Now finally regarding the upcoming lecture, till now we have discussed about the stress systems. So in the upcoming lecture we will try to solve some of the problems related to this, as well as we will try to understand the Mohr-Coulomb theory. There is a theory called Mohr-Coulomb theory, how it has been implemented to this particular shear strength. We will try to understand that. Okay. And now thank you very much, thank you for this particular lecture. Hope you have clearly understood this, and okay, that's it for today. Thank you, have a nice day.